Hello, everybody. So chapter 3 is done, and now we move into chapter 4, which is applications of the derivative. So as you can imagine, calculus has many applications, and differential calculus has a lot of applications in particular, and that's the content of chapter 4. In section 4.1, we are going to start this chapter with the topic called related rates. Now, these are problems, in particular word problems. I know you have this sort of reaction against that phrase, word problems, but these are word problems using calculus, and they are really cool once you master the concept, okay? So let's get started. This is one of the most fascinating aspects of using calculus in the real world. So let's get to it. It's related rates. Calculus is a study of change of quantities. So things change, right? And so oftentimes we describe how things change using functions. And the functions, we have been saying y is equal to x of f of x, but often that change happens, of course, with respect to time. I mean, the word change means that things are changing. And when we say that, usually we think of things changing with respect to time. So the time t is often the independent variable in the section on related rates. All right. So whenever I write WRT, that stands for with respect to. This is a sort of a standard abbreviation in mathematics. And so with respect to time. And anytime we take the derivative in this section, it is typically with respect to time. If you remember that, I think it's going to help us a lot. Now, what kind of things change, right? So for instance, when something spills, let's say an oil spill happens in ocean. And so, the circle where the ocean water is contaminated by the oil gets bigger and bigger, okay? And then the rate at which the circles get bigger sort of depends on how fast the oil is spilling, right? But then the radius is changing, and so is the area. Are they increasing at the same rate? And it turns out, they are not. And how do you know how those rates are related? And that, of course, is where the words related rates come from. The rates are related to each other, but not at the same rates, right? Let's say you have this like a spherical ice or a snowman melting. Now, when as an ice melts into water, this gets smaller and smaller, right? The volume gets smaller with respect to time. The surface area gets smaller with respect to time, and so does the radius, but they do not decrease at the same rate. So how do you figure this out? All right. So the idea is to start with an equation. Okay, and I will give you maybe 3 or 4 examples, and then you hopefully learn the concept and the general outline of how to solve these problems, and then you get to solve a huge number of problems in this section, right? So here's a general guideline. Every problem is different. So I can't give you, this is the formula. We don't have like one formula, such as the product formula, to answer all of these questions. But here's a sort of a general guidelines to follow. Number 1, you start with an equation. Okay. Oftentimes it's a geometric equation or equation that is based on something that we have studied, and then we differentiate. And here is the important part. We differentiate with respect to time. Okay, and that's what I was talking about here. And then you plug in the given information. And then number 4, you solve for the unknown rate. Okay, so like I said, you can't, there's no one way of doing this. You have to be flexible, but this is the sort of a guideline. And the way to learn these, how to solve related rates problems is really just by doing a few In fact, maybe doing a lot. Okay, so here's the first problem. Okay, I'm going to go ahead and write down the problem, and so you can read it and get started. Okay. All right, so here's the first question. Let's say there's an oil spill on the ocean, and the spill is spreading at 100 square feet per second. All right, so every second, the area contaminated by the oil is increasing at a rate of 100 square feet per second. All right, so you can imagine this oil or the circles, bunch of circles, concentric circles, getting bigger and bigger. Okay, that's what the oil spill looks like. And by the way, anytime you have this, it doesn't have to be an oil spill. It could be something else that is circular, that is spreading. This mathematics could be applied in many circumstances, right? And in fact, that's the power of mathematics and calculus in particular, because our tools are abstract, they can be applied in many, many different situations, right? As people say, the power of mathematics lies in its abstraction. Okay. All right. So what do you know? All right, so let me look back at the guideline. First, we want to come up with an equation. All right. So take a look at this. We have the spread at 100 square feet per second. This is the a statement about the area, right? So let's call the area A sub t. And the area is increasing at 100 square feet per second. Okay. Now we have the radius, of course, and radius and area are related to each other, right? This is also in feet. All right. How is the radius related to the area, and vice versa? That's how you think of this equation. That would let you get started on this. Of course, the area, as you know, is pi times r squared. Okay, so this is the starting point. You start with some equation that's given. By the way, this r, radius is changing. So let me go ahead and write it this way, just to emphasize the fact that both a and r are related to each other. Now, they do not change at the same rate with respect to time. And that is what, but the rates are related. Okay, and that's again why we call this a related rates problem. All right, now when we differentiate this, you can do a prime if you like. What I would like to do here is, again, to emphasize the point that we are differentiating with respect to time t. I suggest you write, and I also will write, dA over dt. Okay, this is on the one side. All right, so if you differentiate this other side, of course, you get 2 pi r t to the first power, of course, and then using the chain rule, because we are differentiating this with respect to t, you have dr dt, right? Now, again, this is just applying the chain rule, implicit differentiation, if you will. And then there are a few things you know. A couple of numbers are given. We know, let's say we know, and in fact, you can write this at the beginning, like given in the problem is that the derivative of dA dt. You know what that is? It's 100 square feet per second, and that is the first thing that was given to us. And then the second thing is that do we know dr dt? No, we don't. That's what we are trying to find. You see that? And by the way, this is the skill that you are trying to obtain or polish in this particular section. Can you read what is written in English and translate that into mathematics as a language? How fast is r increasing? The question is, find dr dt when r is equal to 10. So at this particular point, r is equal to 10. And by the way, do not enter this over here, okay? Because if you plug in 10 over here, then as soon as you plug in the number, this becomes a stationary thing, and there is no derivative to be considered. All right, make sure you differentiate first, and once you differentiate each side, then you can plug in this number 10. All right, so let's go ahead and figure this out. dA dt, this dA dt is 100, is equal to 2 pi times r. We already know now what r is at this particular point. But again, do not plug this number in until you differentiate first. And dr dt is still left there. And it's good that we have this because that's what we are trying to find. All right, so you can tell dr dt is what? 100 over 20 pi, okay, which is 5 over pi. Now that's a strange number, isn't it? Okay, but that's okay. 100 over 20 pi, 5 over pi turns out to be 1.592. Now remember, this pi is not an abstract concept. It's an actual number. It's a real number. I mean, it's real number. And it is, 3.14 something. So the answer is 1.592. And I don't really care where you round off as long as you have a reasonable number of digits. Usually 2, 3 decimal spaces would be okay. And then you want to make sure you have the right units, okay? We are talking about the radius increasing and the rate of a radius increasing. We have been using feet per square feet and seconds. So this will be 1.592 feet per second. Now again, notice here, if this number is different, let's say if this number is 20, then this will be 100 over 40 pi, and that's going to change the answer, okay? Which means that even if dA dt is the same, even if the area is increasing at the same rate, the rate at which r is changing, okay? And in fact, let me we have solved the problem, but what you want to do sometimes is just to analyze and say, I wonder what happens when r is different. Okay, can you see the pattern here? Can you see and predict the behavior? Okay, so from this, you can also get a complete solution. Okay, so what we have is this dA dt is on the top. And then I'm just getting this, from that equation here. So dA dt over 2 pi r, right? All right, so if this is, and we are given this is 100, the top is 2 pi r. All right, so you can see as r approaches infinity, so as the radius gets bigger and bigger, remember the area is increasing at a constant rate. But as the radius gets bigger and bigger, guess what happens to the denominator? The denominator gets bigger and bigger to infinity. And so the entire ratio or this fraction goes to 0. Okay, does that make sense? Think about this. Does it make sense that the radius, the rate at which the radius is increasing, it is still increasing, but the rate at which the radius is increasing gets smaller and smaller, less and less. Or in other words of saying this is the radius is increasing at slower and slower pace as the circle gets bigger. It certainly makes sense, right? When the radius is small, the 100 feet per square feet per second is a pretty fast growing circle. But when the circle is really, really big, let's say it's a mile long, r is a mile or something, then in order to increase this by 100 square feet per second, that the ratio, the rate at which the radius is changing is going to be very, very small. Okay, because a small change in a large circle is going to give you 100 square feet per second. Okay, so yeah, that's not too bad, right? This is what some people fear tremendously, calculus word problems. Okay, but hopefully you'll have seen that it's really not something to be scared of. Although, I mean, problems could get more difficult. All right, let's do the second part, the second question. Ball inflating. Okay, so let me go ahead and pause this so I can state the entire problem, and then we'll come back. All right, here's the second question about the an inflating sphere or inflating ball. All right, so this ball, and by the way, I highly recommend that you draw a picture for every problem so you can visualize what's happening. Did you hear me? I will keep emphasizing this, all right? Every time you see a word problem, even some other problems, it helps you extremely well if you draw a picture to help yourself visualize what's happening. Okay, so even if you are not very good at drawing, go ahead and try to draw a picture. All right, so you have this sphere and it's inflating at 2 cubic centimeters per second. That's kind of slow, okay? Now, because a centimeter is, like it's less than half of an inch, right? A cubic centimeter is a 1 by 1 by 1 centimeter cube. How fast is the radius increasing when r is equal to 3 centimeters? Again, this is slightly bigger than an inch if you are not familiar with the metric system, so you can have a sort of a feel for what's happening. So it's a slow growing ball, slowly inflated ball. But anyway, let's try to figure this out. Okay, so let's say, maybe you can write the given. What we are given is that, well, what's the formula we have? Formula of what? Okay, so we have the radius. Right? So we have radius is increasing. And so the other thing that's increasing is this volume, right? So the volume, okay, let's write V, the volume, and R, the radius. And in fact, those are the only two things that are changing with respect to time at this point. That's relevant to this question. What we are given is that dV dt is 2 centimeters or cubic centimeters per second. All right. Now, how odd, and then of course R is 3, but again, this is something that you will plug in only after you differentiate an equation, right? What equation are we talking about? Do you know the equation that relates the volume with the radius of the sphere, right? And again, at this point, you may have to review some of your formulas from geometry. The volume of the sphere happens to be 4/3 pi r cubed. Okay. Now I try to make you aware of these, and if you're not, if you don't know these equations, and some of you may not, depending on your background, I will tell you what these things are. And so hopefully you will not be disadvantaged because you don't know these formulas. Some of the basic formulas you should know, like A is pi r square for the area of a circle, area of rectangles, triangles, you should know those things. Okay. But anyway, so this is the equation. Now let's again try to emphasize that V is with respect to changing with respect to time. T is also changing with respect to time. So this is what you get. All right, dV dt, now we are differentiating this. It's 4/3 times 3. Pi is just pi. And then R, the new power is, of course, square because it's 3 minus 1. And what do you have at the end? By implicit differentiation or chain rule, you have dr dt. Of course, these will cancel. This simply becomes 4 pi r square dr dt. All right. Now we are looking. The question says, how fast is the radius increasing? Okay, so we are trying to find dr dt. Sometimes it is helpful if you write down all the given and what you're trying to find, okay, because that will give you where your goal is, right? What are you looking for? And the answer, you're looking for this. You have this given as 2, and everything else is known, so you should be able to figure this out. All right, let me go ahead and write the equation, a general equation, not specific equation at that time, but a general equation for r dr dt. That is the left-hand side divided by 4 pi r square, right? And you are given that the top is 2. All right, so the answer is going to be 1/2 pi r square. All right, so at r is equal to 3 centimeters, dr dt, it is changing, the radius is changing at the very small rate of 1/2 pi times r squared, that's 9. So this is 1/18 pi. And that, if you can just take your calculator out, I think I have the answer. That is going to be, let's see, do I have this? Yep, 1745 approximately. Okay, what are the units? Let's think about this. We have been using cubic centimeters and centimeters for the length, and so it'll be centimeters per second. Okay, so again, this is a sort of a very slowly growing, inflating object sphere, but you got the answer. Let's go back and look at this. You started with a given or known equation. You differentiated both sides with respect to t. You solve for the rate you're looking for. You plug in the number. You got it, right? Okay. So why are we afraid of this so much? Well, I don't know. So I have had students who say, these are really hard questions. They find them quite challenging. And then there are some other calculus students who would say, oh, this is my favorite subject. Related rates was so much fun to learn. So hopefully, you will get to practice these. And by the end of your exercises, your assignment, you'll say, these are cool problems. All right, number 3. Now, this third problem is quite different. You notice that the first two are actually kind of similar, right? So this is another one of those classic problems that you find probably in every calculus problem. All right, let me write down the question. All right, so here's the problem. Maybe I just drew a picture of it. Okay, I didn't write down exactly what I needed to write. All right, so the plane is flying horizontally at the height of 4,000 feet. Okay, and you can see that, and it's flying in the direction of this red arrow, right? And the question is this: how fast is your distance from where you are standing to the plane? That's s. Okay, it's the distance described or indicated by that green line segment. How fast is s? The distance from you to the plane is how fast is it changing when x, the ground distance from you to the tower on the top of which the plane is flying at that point, when x is 3,000 feet. Okay, so here's a picture. The plane is flying at the rate of, or at the height of 4,000 constant, 4,000 feet. This x is of course increasing. No, I'm sorry, x is decreasing, right? X is decreasing. Is it? No, x is actually increasing, right? Because x is the distance from here to the ground distance from where you're standing to where the plane is standing. And s is also increasing, right? So this is a question, right? And then here are some observations. X and s are both increasing with respect to time. And they're increasing at a different rate, right? And the question is, how fast is s increasing? Now, there's something else I haven't given you, and that is the plane speed is 600 square feet. I'm sorry, 600 feet per second. Okay, so that's given to us. All right, so what is given here? What's given is that x and s are both increasing. The speed of the plane, how do you describe that? That would be dx over dt. Okay, because x is this distance between you and where the plane is. It's the horizontal distance between you and the plane. And this is increasing at 600 feet per second. And that's given, right, as the speed of the plane. And we are to find the s dt when x is 300. And of course, you don't plug this in at the beginning, right? You resist the temptation because you still have to write down the equation first. All right, so what is the equation relating s and x and 400,000? And this part is called, mathematical modeling, right? Anything that can be, I mean, you can see here that you have a triangular, a right triangle. Okay, again, this is very different from the first two problems, right? It is still based on geometry, but this time it's quite different type of geometry. It's almost like trigonometry. We don't have to go into trigonometry yet because this is just the Pythagorean theorem. All right, so how are they related to each other? S square is equal to 4, let's go ahead and write down x square plus 4,000 squared. Get that? This is just Pythagorean theorem. Pyth theorem, named after Pythagoras, an ancient Greek mathematician and philosopher, and sort of a religious leader. All right, so now you take the derivative of all of these. Let's say you get ds dt. Whoops, that's not right. It's 2 times s of t to the first power times ds dt, right? Okay, you take the derivative of the left-hand side, and this is what you get. On the right-hand side, of course, this goes away, and the first term, it becomes 2 times x to the first power times dx dt. All right, now you might as well just go ahead and cancel what you see on both sides. And what are we looking for? We are looking for ds dt, right? So we are looking for this. Let's divide both sides by s, and so you have x over s, and of course you have dx dt. Now this dx dt is given, right? And so dx dt is constant at 600. And so the question really becomes this. Now we have 2 unknowns on the right-hand side. We are given that this is 3,000 at the point in question, right? At the point of time in question. We don't have s. So or I should say, so we need to find it, okay? When x is 3,000, what is, I'm sorry, when x is 3,000, what is s? Okay, now that's pretty easy because you have the Pythagorean triple. If this is 3,000, if this is 4, then this has to be 5, right? So s is 5,000, or you can say 3,000 squared plus 4,000 squared, and you will find that that is equal to 5,000 squared. So that part is not too bad. And therefore, the 3 dots indicating therefore, ds dt at this point when x is 3,000 is 600 times 3,000 over 5,000. Lots of zeros. Let's just cross out a bunch of zeros. And in fact, you get 5, right? 600 over 5 is 120. And so the answer is going to be 360. And so that is the answer. Now, what are the units involved in here? It is the rate of the distance, and the distance we have been using is feet. The time is indicated with seconds. So the answer is that the distance between you, the visual distance between you and the plane, is increasing at the rate of 360 feet per second, even though the plane is going away at the distance of 600 feet per second horizontally. Okay, and so that's the difference. Okay, so what do you think? Again, you do not, plug this in until after you differentiate both sides of the equation. And so I hope you're not finding these too difficult. Okay, now if you look back to this particular problem, the only extra step we had to do was to find this. See, this was not given. It was easy to find, but there was a missing number in the equation that we were going to use to solve the problem because this needed to be found out. This was not explicitly written in the equation, but because of the relationship we knew, which was this, when x was 3,000, it was easy for us to find s to be 5,000. All right. We have a few more problems. Let's do a couple more problems before we close the section, and we'll cover these 2 last examples in the second part of this video for 4.1.